All right, let's dive into some cutting-edge research. Today we're exploring deep cross-attention, or DCA.
DCA is a novel architecture. It's built on residual networks, or ResNets, but with some clever tweaks to address a key limitation.
BizNets, right? They're popular, kind of like the express lanes for deep learning. What's the limitation?
Think of it like those express lanes can get so jammed they create a new bottleneck. You see, traditional ResNets, they treat all information from earlier layers as, equally important, and, well, this can dilute important signals as the network gets deeper.
So it's about, like, smart traffic management, not just more lanes.
Exactly. And this paper, it goes right at the problem. They ask, can a residual network easily recover its input? Kind of like retracing your steps. If a network struggles with that, it means information's getting lost.
A memory test for the network. What'd they find?
They did a simple experiment, trained a ResNet to learn the identity transformation, outputting the same data it gets as input. You'd think it'd be easy, but even with those skip connections, ResNet struggled to perfectly reconstruct the input.
So even with the explain, some info gets lost. How does this paper fix that?
They introduce generalized residual networks, or GRNs, enhanced ResNets to, better preserve key information.
GRNs, okay. What makes them different?
Three variations, actually. GRN-V1, it introduces dimension-independent weights, learns the best combo of outputs from all the previous layers. Then there's GRN-V2, which goes further with dimension-dependent weights, allows different features to have different importance.
Getting picky about what info gets amplified.
Yeah, precisely. And then GRN-V3, it brings in input-dependent weights. The weighting adjusts based on like the specific data. The network adapts its information flow, in real time.
Sounds powerful. But how do we know GRNs are better than regular ResNets?
That's where the theoretical analysis comes in. They use a low-rank linear model to compare different architectures. The key metric, excess risk.
Excess risk. Explain it simply.
It basically tells us how much worse a model performs compared to like the absolute best model for the task. Quantifying the gap between a model's performance and perfection.
Lower excess risk, better model.
Right. And what they found is there's this critical threshold related to the collective rank of the layers compared to the input.
Collective rank, input dimension. Bit technical.
Okay, so the collective rank, it measures the total complexity of the layers in the network. Input dimension, that's the complexity of the data going in. What they found is when the collective rank is below a certain point relative to the input dimension.
That's when GRNs, especially GRN-V2, shine.
Precisely. They get a way better balance between accuracy and model size. Basically, same performance with a smaller, more efficient network.
So theoretically, GRNs have advantages. But how do they work in practice?
That's where deep cross-attention, DCA, comes in, the practical application of these ideas, specifically for transformer networks.
Ah, transformers are huge in AI. So how does DCA work within a transformer?
DCA integrates three separate GRN instances within a transformer's decoder block. They dynamically shape the queries, keys, and values, those core parts of the attention mechanism.
Okay, queries, keys, values. They're like the transformer's search engine, like helping it find the important info and all that data.
Yeah. DCA is like an intelligent filter, refining those queries, keys, and values based on the input data. Make sure the attention mechanism focuses on the most relevant parts, improving accuracy and efficiency.
So giving the transformer laser focus.
Exactly. And the cool part is DCA does this without changing the attention mechanism itself. Seamless integration works with any transformer architecture.
Theoretically sound, clever implementation. But how does it actually perform? What kind of results?
They tested DCA on language modeling tasks using two datasets, LME and C4. Huge datasets, for training and evaluating how well a model understands language.
So did DCA live up to the hype?
Results were good. DCA consistently beats standard transformers in perplexity. Lower perplexity means better language modeling performance.
More efficient and more accurate.
Yep. Same perplexity as transformers, but training was way faster. We're talking big gains in efficiency.
So reach your destination faster, but without sacrificing quality.
And there's more. They also tried applying DCA to pre-trained models.
Models that are already trained on a massive data set.
Yeah. Since DCA's changes fit right into the standard residual architecture, you can add it to pre-trained models without changing their initial function.
Don't have to start from scratch. Great for people working with existing models. What were the results?
Adding DCA to pre-trained models led to even more improvements in perplexity. Even well-established models benefit from this dynamic approach.
So we've got improved accuracy, faster training, and it can even enhance pre-trained models. Anything else?
Yeah, one more big benefit. DCA makes training much more stable. It really reduces those disruptive loss spikes that can mess up the training process.
So smoother, more reliable learning.
Exactly. Super important when you're working with large, complex models.
How does DCA compare to other state-of-the-art methods for improving transformer performance?
They compared DCA to other approaches like Laurel, DenseFormer, and hyperconnections. DCA consistently had lower perplexity, so it outperformed those methods in language understanding.
So not just a contender, it's setting a new standard.
Seems like it. They also did a deep analysis of DCA's individual components and ablation study to isolate the contributions of each GRN variation.
Which one was the MVP?
Interestingly, it was GNV1, the one with dimension-independent weights that had the biggest impact on perplexity.
Sometimes the simplest approach works best.
Looks like it. DCA, with its 3 GRNv3 instances, came in a close second, followed by GRND2. But before we finish part 1 of this deep dive,
We've only looked at language modeling so far. DCA can do more.
absolutely, lots more to explore. So let's talk about computer vision, specifically how DCA can improve vision transformers, or VTs.
VITs, right. Transformers for images, they've done amazing things in image classification, object detection. But can DCA really make a difference with visuals?
That's what the researchers wanted to find out. They thought DCA's, ability to dynamically adjust information flow could be just as useful for computer vision as it is for language.
So those filters, the ones that amplify or suppress signals based on relevance, they could work on images too.
Exactly. Think about it. Different parts of an image have different levels of importance. If you're trying to identify a cat in a picture, the pixels outlining the cat are way more important than, say, the background pixels.
Like our brains focusing on the important parts of a scene, ignoring distractions. Is DCA doing that for VTs?
You got it. DCA helps the VT prioritize the most informative parts of the image, so it doesn't waste resources processing irrelevant stuff.
Sounds efficient. How did they test this? Did they use a specific data set for computer vision?
They used ImageNet. It's a huge data set, millions of labeled images, thousands of categories, like the gold standard for testing image recognition algorithms.
ImageNet. That's a tough one. So how did DCA do? Did they have to change its architecture to work with images?
Yeah, they had to make some adjustments. Remember how DCA worked within the decoder block of a transformer for language modeling?
Right. Shaping the queries, keys, and values for the attention.
For VTs, it's a little different. Images are 2D, so they're first split into smaller patches, which are then treated like tokens, kind of like words in a sentence.
So each patch is like a piece of a visual puzzle. DCA helps the VT put the pieces together smarter.
Right. DCA is integrated into the transformer blocks that process those image patches. This lets it dynamically adjust the information flow between them.
So instead of treating all patches the same, DCA picks the ones that are most important for the task, just like it did with words.
Exactly. And the
Oh, wait. Someone wants to join. Hey, go for it.
I know this work do a lot of theoretical analysis. So what's the intuition of this proof?
Okay, that's a great question. It's easy to get lost in the math. Let's break down the core intuition behind the theory.
Yeah, let's unpack this. We talked a lot about the what, but now it's time for the why, especially with the proofs they use.
The key is understanding why traditional ResNets might struggle. It's all about how information flows and whether a network can easily reconstruct its input, even after many layers.
Like if you try to retrace your steps, but you've lost the map.
Precisely. The ResNet, despite its skip connections, can lose some of those original details. The proofs are designed to show that GRMs, especially V1 and V2, do a better job of retaining this info.
How do they do that?
Well, think of it this way. The standard ResNet treats all information from previous layers as equally important. It's like taking a group photo and giving everyone the same amount of focus, no matter who's in it.
So some faces are more blurry than others.
Exactly. Now, GRNs, especially V2 and V3, are different. They learn to give each piece of information the amount of focus it deserves.
So you get a sharper picture where everything is crisp and clear.
Yes, the proofs mathematically show that by carefully weighting different dimensions, these GRNs can reduce the excess risk, that gap between the model's performance and perfection.
It's about reducing the information lost as it travels through the network.
Exactly. And those theorems, like the one about the excess risk, they give us a way to quantify this improvement. It is the theoretical foundation that shows us that GRNs offer a better trade-off between accuracy and model size.
So it's not just about adding more layers. It's about adding them in a smart way preserves the original information.
Right. The analysis of the model rank and the low rank assumptions, they're important. They essentially capture the idea that the information in each layer is often redundant.
Like there's a core signal with a lot of noise around it, maybe.
Yeah, the idea behind GRNs is to filter out that noise. The math behind all this, it validates the intuition that these GRNs are better equipped to recover information compared to standard ResNets.
Okay. That makes the math less daunting now.
And keep in mind, this theoretical framework gives us a solid foundation for designing better deep learning architectures.
So it's not just math for the sake of math. It's math that makes smarter AI.
Exactly. Now that we've covered that where we were, the paper also found that DCA significantly improved VIT accuracy. Oh, yeah,
So what's the risk model for?
And you're right to bring it up, especially after diving into all the theory. When we talk about excess risk, we're talking about the risk of a model performing worse than the best possible model.
Yeah, like even if a model is good, it's not perfect. Excess risk is the difference between what's possible and what our model is actually doing.
Right. So the proofs aren't about some kind of risk in the real world, like in the insurance sense. They're about the potential for error in the model itself, how far from optimal it is.
So the risk is how far the model is from ideal performance, not like a safety risk. It's more about the model's accuracy and efficiency.
Exactly. And the researchers use math to analyze, how GRNs can reduce this inherent risk or potential for error compared to standard ResNets.
It's about quantifying how well the model is performing and making sure we're not leaving performance on the table.
Precisely. And getting back to the main point where we were, the paper also found that DCA significantly improved VIT accuracy on ImageNet better than standard VT architectures.
So DCA's filtering works well for visuals too. Why does it work so well, does the paper say?
They say DCA helps reduce something called attention dilution in VITs.
Attention dilution. That sounds familiar. Is it like the information dilution we talked about with ResNets?
Yeah, they're connected. In VITs, attention dilution happens when the attention mechanism spreads its focus too thin across all the image patches, even the unimportant ones.
Like trying to read a page where every word is highlighted. You wouldn't know where to look.
Exactly. DCA is like a smart highlighter, picking out the key words, making the text easier to understand.
So DCA helps the VT focus on the important image patches, filters out the visual noise.
Precisely. This leads to better feature extraction and, in the end, higher accuracy in things like image classification.
It's like DCA is giving the VT glasses to see. Did they compare DCA to other methods for VTTs? To see how it stacks up against the competition.
They did. They tested DCA against some state-of-the-art techniques, including ones that try to, improve attention in VTs.
And how does it do in this visual showdown?
DCA won. It consistently had higher accuracy on ImageNet than the other methods, and it also converged faster during training.
So it's not just more accurate, it's also more efficient to train. Impressive.
It shows how powerful DCA's core principle is, adapting information flow to the task, whether it's language or vision.
Okay, so we've covered language modeling and computer vision. Any other areas where they tested DCA?
Yes, they also looked at DCA's potential in audio processing.
Audio processing, that's a whole different challenge.
All right, welcome back. Let's wrap up our deep dive into DCA.
Okay, so we've seen how DCA works for language and images. Now we're talking audio processing. What makes audio so tricky for techniques like DCA?
Well, audio data is different from text or images, right? It's temporal, meaning the order of sounds is important. And it can be really complex, like all the layers of sound in a song or the subtle stuff in human speech.
So how do you even apply something meant for images or text to audio?
It starts with how you represent the audio. Got to convert the raw audio waveform into something a transformer can understand. Usually involves spectrograms or something similar to capture how frequencies change over time.
Turning sound waves into a visual representation, like sheet music for a neural network.
Exactly. And once you have that, you can use those DCA principles. Those dynamic filters can now prioritize important stuff in different frequency bands or at different times within the audio.
So DCA could focus on the frequencies for human speech and filter out background noise, like a noise-canceling headset built into the network.
That's a great way to think about it. And they tested DCA on, speech recognition, music classification, different audio tasks.
What kind of data sets did they use for audio?
For speech recognition, a huge data set of transcribed speech, like tons of podcasts with text. And for music, a data set with lots of different genres.
So did DCA keep up its good performance in the audio?
The results were, similar to the other areas. DCA made transformers better at both speech recognition and music classification. Higher accuracy than standard transformers, even with how complex audio is.
So DCA is like a triple threat: language, vision, and now audio. This idea of dynamically adjusting information flow seems pretty fundamental, huh? No matter what kind of data you're dealing with.
Yeah, seems that way. Shows how versatile DCA is and its potential in, all sorts of applications.
Like DCA can become an expert in anything, kind of like our brains. Did the researchers mention any limitations or downsides to DCA?
They did mention a few areas for further research. One is the computational cost. DCA doesn't add tons of extra parameters to the model, but those dynamic filters do need some extra processing power.
So you get better performance, but maybe a slightly higher computational cost.
Right. And hey, yeah, what's up?
Can we wrap up the conclusion into one sentence?
Absolutely. Let's sum up the core idea of DCA in a single sentence for you.
Okay, so in essence, deep perception enhances transformers by dynamically adjusting information flow, leading to better performance.
There you go. That hits the highlights. We were just about to wrap up the show, so let's keep going.
Yeah, getting back to where we were, the researchers also emphasized testing the generalizability of DCA.
Right. Like,